This is part 7 of the series Right Triangles and Trigonometry, and in this part we're continuing with examples of the geometric mean, leg, and altitude theorems. In this example we have a right triangle and we're given the altitude AD and we're looking for the segment BD on the hypotenuse. Again, this is classic signature of the geometric mean altitude theorem. So that's the way we're going to set it up. And in this case, we know what the geometric mean is because the altitude is the geometric mean. So here we have the proportions set up. The geometric mean is 8 because that's the altitude. And it's the geometric mean of the segments on the hypotenuse. So x and 12. So x equals 8 times 8, which is 64, divided by 12, which simplifies to 16 thirds. So that was a relatively straightforward one. Let's move on to the next problem. In this problem, we have a very different situation. We don't know anything about the altitude here, but we know the two segments on the hypotenuse, and we're looking for this leg AC. This is a classic signature of the geometric mean leg theorem. When you have the hypotenuse broken apart and you are looking for or know one of the legs of the big right triangle. So the geometric mean leg theorem states that the leg is the geometric mean. So it's another geometric mean problem. We set it up just like we always do. And the leg is the geometric mean, so it goes in second and third proportionals. And it is the geometric mean of the entire hypotenuse, which means CD plus DB. So it's going to be 4.8 plus 15.2. And the segment on the hypotenuse closest to that leg, or adjacent to that leg, 4.8. So now we have to do a little bit of algebra here, and we're going to have 4.8 times 4.8 plus 15.2 equals x squared. Now we're going to take the square root of both sides, so x equals the square root of this whole thing. 4.8 times 4.8 plus 15.2. And again, I'm doing this purposely. I'm not simplifying this ahead of time because I just want to enter this one time in my calculator. So we're going to have the square root of 4.8 times 4.8 plus 15.2, close my parentheses, and our value is 9.79 or 9.8. So x is approximately equal to 9.8. Well, just as a quick recap, what we did was we determined this was geometric mean leg because we had a leg and the hypotenuse was broken apart, and we set it up so that the leg is the geometric mean of the entire hypotenuse, so we added these two together, and the segment on the hypotenuse adjacent to that leg, 4.8. And I didn't add these ahead of time, I just copied them down so that I could enter them at one time. Now this is the preferred way to solve if you're looking for an approximation. But wherever possible, you're going to want to give exact values. In this case, this comes out to x equals the square root of 96, and so we would have to simplify this. So that becomes 2 and 48, 2 and 24, 2 and 12, 2 and 6, 2 and 3. So we got quite a few 2's here. We have 1 pair, 2 pair. So that's 2 times 2. And we have 2 times 3 that are single, so they're going back in as a 6. So that's 4 square roots of 6. So the exact value of x is 4 square roots of 6, and the approximation is 9.8. So let's go on to the next example. In this situation, again, we don't have anything for the altitude, but we do have a leg, and the hypotenuse is broken apart. So that means we're going to be using geometric mean leg theorem. And let's go ahead and set that up. It's a proportion, so we go ahead and write our proportion. And the leg is the geometric mean, so it goes in the second and third proportional positions. And the leg is the geometric mean of the entire hypotenuse. In this case, it's going to be 17 plus x. 17 plus x. And the segment on the hypotenuse adjacent to the leg, which is 17. Now we're going to have a little bit more algebra here to solve this. So let's go ahead and cross multiply. 17 times 17 is 17 squared. 17 times x is 17x equals 22 times 22, so that's 22 squared. Now we're solving for x, so 17x equals 22 squared minus 17 squared, and then we're going to divide by 17. So x equals 22 squared minus 17 squared over 17. Now you'll notice in this case there's no radicals because we didn't actually have an unknown that we had to take the square root of. So we're just going to put this in our calculator and see what we get. So we have 22 squared minus 17 squared divided by 17. That gives us 11.5 approximately. And there's no exact value for this one. So x is approximately equal to 11.5. Let's go ahead and do one more example just to make sure we've got this locked in. In this problem, we have a very similar situation, but it's going to be different from a solution standpoint. Notice that we have the leg, and the hypotenuse is broken up, but notice that the segment adjacent to the leg is our variable this time. And that's going to create a little bit of a complication for us algebraically. So let's go ahead and put this down and see how this solution comes out. Again, it's geometric mean leg theorem because we have the leg and the hypotenuse is broken up. So it's a proportion. And 8, the leg, is the geometric mean of the entire hypotenuse. In this case, it's x plus 4. So x plus 4. And the segment on the hypotenuse adjacent to the leg. In this case, that's going to be x. Now we go ahead and, as usual, we're going to cross multiply here so that we can solve this thing. X times x is x squared. X times 4 is 4x. And that equals 8 times 8, which is 64. Now here you can see we have a quadratic equation. And so in order to solve this quadratic, we're going to have to get everything on one side and put it in standard form. So x squared plus 4x minus 64 equals 0. Now let's see if we can factor this guy out. So we have x and x plus and minus. It's difficult to tell which one is which. It doesn't really matter. If this sign is negative, these signs are different. If this sign were positive, these signs would be the same, and they'd be whatever that sign was. In this case, it's negative, so they're different. we need two numbers that multiply to give us 64, but add up to give us 4. In this case, it doesn't look like there are any because we can't use 32 and 2, we can't use 16 and 4, and we can't use 8 and 8. So there are no integer values that are going to satisfy this. So let's resort to the quadratic formula. So it's negative b plus or minus the square root of b squared minus 4ac all over 2a. That's 1. So now this discriminant is going to come out to, this is going to be 272 and negative 4 plus or minus that over 2. 272 is going to simplify to 2 and 136, 2 and 68, 2 and 34, and 2 and 17. So these are our prime factors, and we're going to have two pairs, so it's 2 times the square root of 17. So this is going to be negative 4 plus or minus 4 square roots of 17 all over 2. We can cancel out a 2 here, so that's going to be negative 2 plus or minus 2 square roots of 17. So these are our exact values. Now, since we're looking for a side length, an x, we can eliminate the negative square root here. So our value is actually negative 2 plus 2 square roots of 17, which is approximately 6.24. Now, we could have done this another way. If you happen to be lucky enough to have a TI graphing calculator or some graphing calculator, doesn't have to be a TI, you can plug this equation, this quadratic in, x squared plus 4x minus 64, and you can have the calculator tell you what the zeros of the function are. So we hit second, trace or calc, and the zero function, which is option 2. It graphs the function, and you can see it's going to have a negative thing over here, and it's going to have 1 here. So we pick the left boundary, that is, some number to the left of where this graph is crossing the x-axis. I like to use 0 whenever possible, so it's 0. And a number to the right of where it's crossing. This is 0 and this is 10. So let's just go ahead and pick 10 and let the calculator guess. And there it is, 6.246. So you could have used the calculator if you happen to have one of these. If you don't, you're going to have to resort to this method or one of these methods to solve for your quadratics. All right, well, that wraps up the right triangle similarity theorems. And in the next part, we're going to start with trigonometry. So you're most definitely going to need a calculator that has the functions sine, cosine, and tangent on them. It's also going to need this strange looking thing here that says sine to the negative 1, cosine to the negative 1, and tangent to the negative 1. It doesn't have to be a graphing calculator, but it needs to be a calculator that has some memory capability and that has these 3 trigonometric functions. All right, I will talk to you in the next video.